Thank you very much for having me. I can always appreciate conferences where I can actually present in shorts, t-shirts, and sandals. That makes it very nice. For everyone who doesn't know me, I'm co-founder and currently VP of research at a company called iVerify. We develop software to detect commercial spyware at scale. And this is pretty much the talk that I'm also going to chat about today. I do like iOS malware and exploitation, and I also play basketball and board games a lot. Today we're going to talk about a bit of the history about Siteworks Predator spyware. We're going to do the first part of the sample analysis together, and we're going to have a short outlook and also looking at some of the security mitigations that Apple added and how we can actually detect Predator right now. So let's go into the history first. A couple of definitions first. First is, what is commercial spyware? This is usually an offensive capability that is provided by companies for nation states. So it should be used to fight things like terrorism, so on and so forth. It usually comes with a spyware implant used for data exfiltration. They use zero-click or one-click exploit chains, which means if you have a zero-click, you just need to know a phone number and email address of a target, and you can just infect that phone if it's available to the network. And very often they use zero-day exploits, so they can even infect devices on the latest operating system, and they usually infect individual targets. There's more research on it, and very often they are also referenced as private sector offensive actors or mercenary spyware. Why do I specifically like to talk about commercial spyware? Because over the past, we have seen there is multiple known abuses against civil society, journalists, business, and also governments, where commercial spyware was not used in the intended way. And obviously, from a technical standpoint, there is non-trivial detections on iOS, and very often you can see novel or interesting vulnerabilities and exploits used. And these infections are mostly low in probability, but they have a very high impact of the person. If your phone gets infected by Predator, by Kandero, Paragon, or by Pegasus, you can assume that all the data of your phone is compromised, including passwords, camera access, microphone access, pictures, banking, so on and so forth. So when that spyware is on your phone, they can pretty much use the phone as you would do it as well and do what they want with it. Let's talk about a couple of recent reports about Predator malware. We'll start with pretty much the Predator version in 2021, when we had the first public surfacing of that. At this time, the malware was using an infection vector, which was WebKit. So this is essentially the Safari browser. It was detected by Citizen Lab and analyzed by Google Tag and Cisco Talos. It was attributed at the time to Intellexa and Siteworks, and there was a couple of IOCs like processes, files, shortcuts, and URLs. The interesting part about that was that there were a lot of firsts, especially with Predator. There were first business persons which were publicly attacked by it. There were a lot of US politicians which were attacked by this kind of malware, and obviously journalists. And there was a case, and I can only recommend reading that report by Citizen Lab, where a phone was attacked by Predator and Pegasus at the same time. So let's go into the technical details here. What we could see is that there were two processes which were executed by the Predator malware, and both of these processes were coming from a directory, private var temp, where processes on iOS usually are not spawning from. The reason why threat actors are using these processes are, one, it's a process that's on the system partition, and applications are not able to read from that directory, and two, this process gets flushed out on reboot. So even if you're kind of missing the point where you should leave the device, if the user decides to restart the phone, the malware would be gone. Very often, if there's indicators for malware, the first thing that security experts, people usually tell them is reboot your phone. But if you reboot the phone and the malware is gone, you don't have any forensic evidence anymore available that you can find the infection. Additionally, this malware was also using a couple of other binaries or injections. There was an agent.dlib file, there was a hooker or take photo binary that were used as well. Citizen Lab didn't disclose what they were exactly doing with those specific agents or binaries, but that's the only thing that we got from there. Based on the report, we could also see there was a command line argument, which was called payload2, and then there was a URL. This part of the binary was still executed with a kernel taskboard and a PID. A kernel taskboard is a mechanism that would allow you to read and write memory inside of iOS. This is something that is not possible more on later versions. And what we could also see is there is a responsible process or a coalition which tells us that this specific process was started by ZeroActionsD. ZeroActionsD is the background process that is responsible for executing shortcuts, which was also a hint that this was used as a persistence mechanism. Responsible processes or coalitions are a pretty much iOS, macOS concept, but you can think about this as a parent process that has spawned or was responsible for spawning that other processes. And there was a couple of activity that we could get from the report. They were using a configuration directory that was residing on the user space partition and private logs keybackd. They were stopping the shutdown process, so they were leaving behind traces inside of shutdown log. They had a persistence module, and they were using a Python loader, so the whole malicious activity was written completely in Python and was actually shared between the iOS and Android sample. So inside of the iOS sample, you could also see Android code and vice versa. And they were using extensive logging. So every time that this app was executing, they were saying like, hey, Predator is installed, let's run it. Hey, Predator is doing XYZ. Hey, Predator is here. And if you have listened closely to the talk before me, inside of Unified Logs, you could have seen all of this. So there's forensic sources where you can just like, they're essentially like spraying messages like, hey, we're on the system. But still, it took a lot of time until Citizen Lab or also TAG were able to actually find them. In terms of other activities that we have seen, there was a locale checking. If the device would be in the broader region or it would have like language settings for Israel installed, they would not infect that phone, which also makes sense because SiteDrogs was developed by Israelis. And what you could also see, there is no DACT code removal. That means you had very often functions and other parts which are actually not used anymore, but the code was still visible in the sample. So you could analyze and understand more what it's doing. In terms of cleanup, what they did is essentially launching from private var temp. They have another process, the helper, that was spawning there as well, and they would be disguising as normal system processes. Even at the time, it was already pretty much public that there is databases and backups, so on and so forth, where you can see processes that are like consuming network connections. But they were using process names like COM Apple WebKit Networking, which is absolutely fine to do network connection because that's its job. Or even user event agent. So if you did not have the path information available, you could not distinguish those specific processes from the rest of the system. And last but not least, they were removing crash logs. Okay. We're going to revisit that data later on when we're comparing the new version of the sample with the 2021 version. So let's move to Predator in 2023. And the first information that we got that there is a new version or a potential new version of spyware was actually by the iOS 17.0.1 vulnerability disclosure, where there were like 3 vulnerabilities which have been solved. On a day later, Google TAG also released a report that these vulnerabilities have been used by commercial surveillance vendor in Egypt. And even on the same day later, Citizen Lab shared that this was also Predator. So Google gave us a little bit more information on the actual vulnerabilities which were used. There was a certificate validation issue inside of CoreTrust. There was a local privilege escalation which allowed an attacker from going from WebKit to kernel. And there was a remote code execution that they used to get actually onto the device with Safari with the browser. Google said, we're planning to publish a technical deep dive on these exploits in line with the Google Vulnerability Disclosure Policy. I'm still waiting for that. I don't want to call them out, they're doing amazing work, but it would have been definitely nice to get more on that. But luckily, because the bug was in CoreTrust, we actually had a couple of smart people, one of is sitting over there, that reverse engineered and patch diffed the bug and found out how it is using and implemented that bug inside of TrollStore, which you can now use to run side-loaded applications with pretty much arbitrary entitlements. And I hope you have listened to Lars's talk later, or like earlier this morning, because he has an excellent summary of how this bug actually works. So I'm not going to go into any more details. Then there's another very interesting blog post that Google published actually on that vulnerability. This was just last year in August, where it was found that the specific vulnerabilities that Predator used was found by a Russian state actor who was abusing a similar exploit to target people in Mongolia. They didn't run an implant, but they just used that specific exploit to target WebKit and extract the cookie database. What they found is that the exploit were so similar in the development that it is very, very likely that they are coming from the same person that developed it. So the question was, what is the link between then Predator, who was using that exploit, and the Russian threat actor that were using it as well? They have a couple of theories on that, but we don't have an answer yet. But it is definitely not the first time that we're seeing that some of the commercial spyware exploits are also going to be used in other campaigns. What I found interesting on this campaign is, and if you are rethinking the vulnerabilities which were also disclosed, is that they could also easily just write their own implant and launch their implant, because there was a local privilege escalation that was fixed on the same version, and there was the CoreTrust bug. And even at the time, even the public implementation of the specific exploitation of the CoreTrust bug was available. So they deliberately decided to not go down the route of running an implant and just staying inside of WebKit. It's probably something we're going to see more. That's all that we have for the vulnerabilities. So the kernel exploit or the kernel vulnerability, no one reverse engineered that or talked about it yet. But we got a bit more information on the actual loader and the actual sample that they were able to recover. So in September 2022, they started the first publication of that. So we did also then definitely know that it was Predator. And in October 9th, so the date on the slide is not correct, they were starting to tell us a little bit more information what they found on the sample. But Citizen Lab only covered the so-called validation steps that Predator was using. So they were checking for running processes from private word temp, which is pretty interesting in that way, because there's only two possible explanations for that. It's either they're checking if they themselves have already tagged the device and they're still executing from that directory, or they're checking if anyone else is executing on the system from that directory. That's the only possible explanations on that. Then they were checking for log monitoring, which is if a console is attached to it. They were doing some rudimentary location check, which was basically the same as the locale. They were checking if developer mode was enabled on the device. And then they did some additional steps for jailbreaking detection, for monitoring, for proxies, and for man-in-the-middle. But they have not fully disclosed what the details of that implementation are. So if we're summing this up, we're getting pretty much to this picture. We have some of the information available, but we're definitely not seeing the clear picture of what Predator was doing there and how it was operating. And the most important question for me or for anyone else from a forensic standpoint is, what are the IOCs that we can use in order to find this malware, like in the wild or even on old iOS devices? So if we're summing up the chain, then we started with WebKit as an exploitation vector. We had a potential kernel exploit that was coming afterwards. We don't know if it was exactly that order. Then we have the loader that we do have a little bit information about, and a potential implant, and maybe potential persistency as well. All right. So let's look at the sample. And I'm very happy that someone that is able to stay anonymously in the second half of 2024 graciously donated a sample of that loader to us so that we can do some of the analysis. And it was a loader of the Predator 2020 CLM sample. So what we decided is, in terms of analysis strategy to follow, is to try to do a mixed approach of static analysis, dynamic analysis, and network analysis. And essentially using tools like Command Line and IDA and Ghidra to do the static analysis, and then use something like Frida, a Jailbreak, or TrollStore to go on for the dynamic analysis. Unfortunately, and we're going to see that, I didn't have any applicable device available that I could use for dynamic analysis, and I don't know how often I've asked Apple to get a security research device to do this kind of work, which is kind of painful. So if Apple is here, I still have a wish for 2025. Yeah, so that's also the reason why I'm going to focus most of the time today on static analysis, and we're going to start with that right now. What I'm usually using as a first point is just running strings on a potential sample. And if we're running strings here, we're pretty much clearly also seeing directly the reference to the developer mode status. We're also seeing a couple of other references which are probably also visible inside of the checking logic. And if we're that's the same. And if we're going a little bit further down, what we're going to see is a couple of iOS build numbers which are coming up. And a bit later, we're going also to see a couple of iPhone modules. Without any knowledge of all what the sample is doing or not, but it is likely that these might be in some way associated with the actual build versions which are supported, or with the iPhones which are supported by the specific malware as well. There's obviously no proof without actually analyzing it, but it does give us a good experience, or like a good implementation of that. Now, a second tool that I'm always using as well is running OTool. OTool gives you a lot of information about a Mach-O binary, which is the default binary format on iOS and macOS. And with OTool -large L, we can see what are these linked libraries to it. And we can immediately see here that they're calling on CallKit and Audio Toolbox, which are pretty much two frameworks that are definitely associated to audio recovering, or maybe even calls, which are used. So potentially, this sample has the capability of already recording audio or even intercepting calls. Now, if we're looking at all the load commands, we can also see what is the minimum OS that this specific sample supports, and what is the SDK what it was built with. So here we can see that this sample is supporting iOS 16 and upwards, so which means if you would run it on a 15 or even on a 14 device, it is not potentially working. Okay. Now, because we already know that this was a loader, I wanted to check the code signature to see if we can find the specific implementation of the CoreTrust vulnerability. But if we're running Apple's CodeSign tool on it, we're only going to seeing one signer, which is kind of interesting. But we're definitely going to see that one of these signer has an identifier. It's called Watcher, and what we're also going to see that this is a SYN binary, and it's only having one architecture, which is ARM64E. Which means it's only going to be working on some of the devices that would support iOS 16. It's not going to working on every device. Which was also some of the issues, because the iOS 16 devices that I have were all ARM64 devices, which were still jailbreakable with Checkbrain. Okay, so this one signer is a little bit weird. We would get some team identifier or some of the other information available, but we're definitely not going to get the full picture. Luckily, there is other tools available, like Disarm from Jonathan Levin, which allows us to look at the code signature in total. And the first thing that we're going to see here is the first code signature, which is actually going to be a copied signature from a valid from a valid App Store directory. It works exactly the same way that Lars described it this morning. And the second signature that we're going to see is the one that also CodeSign showed us, which is here where the watch identifier is. Interestingly, it's a little bit different version of the code signatures that it used, but we can also see the exact timestamp when this binary was actually signed, which was still somewhere in September 7th. Okay. The next thing I did afterward is looking at the entitlements. Entitlements are telling us what are privileges that this specific application could potentially use, and it used a lot of entitlement, and here are a couple of the ones which are interesting. For example, they used the security no container one to get a sandbox in Cape. They had the CS disable library validation for a potential library injection, and a couple of other entitlements which were giving them a little bit broader access. The one that I also found interesting is the allow obliterate device, which I don't know if it's actually allowing you to wipe the device or not, but it's definitely a capability I would not want to have on any kind of commercial swiper. When I was looking into the different function names that are available, what we can quickly see is there is a couple of Objective-C functions that are available, a couple of foundation frameworks which are there, and then we can also clearly see that there is a lot of the code, there's pretty clear function names which are visible. which also makes it pretty clear what we want to do here is we have 3 different programming languages that we need to work with, which is Objective-C, C, and C++. We have a lot of interesting functions to cover, and we have no obfuscation. So that is pretty much actually a really easy reverse engineering task. My strategy for working with IDA and Ghidra, because I'm not a full-time reverse engineer, I deal a lot with forensics and other stuff, but I just do this more as a hobby, was essentially just load this up in IDA, look at the function itself, let's use an LLM to take the disassembly from IDA to generate some source code, try to get an understanding of it, even if it's not perfect, but then let's change the code in IDA to have better naming conventions, and I can change it across the entire program, and then just like gear continuously. And actually, for me, this worked pretty well. That might not be super readable, but just using this, the LLM was actually able to translate a lot of the variables back into a proper naming. It removed a lot of the boilerplate code in IDA, which is for me hard to read as I'm not just like a used reverse engineer. But it is pretty much, it allows it to just like tears it down to pretty much normal function code. It takes a bit more time, but it is pretty fine. Okay. This allows us now to look at the actual overview of that main function of the Predator binary. So the first thing that it does, it gets spawned with like 14 command line arguments. Then it's going to copy those arguments. It's going to initialize a local variables for the function. And then afterwards, it's going to check if arg1 to 13 exist. And if they do not exist, it would go into exit. And then afterwards, it's be zeroing in out. You remember the Predator 2021 sample where the command line arguments were pretty much visible inside of the forensic artifact? This is not going to happen again because they're now just like clearing them out. And then they're checking if the arg14 is going to be watcher. And if that's not the case, then they're going to exit. And afterwards, they're going to initiate the watcher, the watcher name class and the watcher struct, which is the watcher class essentially with a helper. And then afterwards, they're going to spawn watcher. They're going to start it, which is going to be running in a run loop, like continuously. And if it's finished, it will going to exit. And then afterwards, they're going to check if then it's turned to helper. And if it's turned to helper, if it's not helper, they would exit. And if it's helper, they would initiate this with read-write. What this is essentially doing is getting a kernel read-write primitive from the previous exploit stages, and it would be used in the helper functionality. And depending on if watcher is first found or not, they would immediately also like run the helper functionality. If the init is failing, that specific function would also exit as well. Afterwards, they're going to start the helper, which is also going to be running in a loop. And then there is going to be an exit success. So the summary of what we can see in the main, in the first main function is that there's going to be 14 command line arguments that we need to reverse engineer. The 14th one is going to tell us what is the exact mode that this is running, and then we know that we're going to have 2 dedicated processes, a watcher and a helper process, which are going to be running continuously in the background, and watcher is very likely going to be the first mode that is executing. Now, let's look a little bit deeper into what actually happens after the watcher init. It's going to call the spawn function. It's going to call a copy watcher function, which is going to copy the actual binary of watcher, which is in memory, to disk. It's going to run a couple of checks. And if those checks are failing, then it's going to report to the server back that these were failed. These are the exact validation steps that Citizen Lab also detailed before. If those are all succeeding, it's going to download an executable. It's going to check the agent. And there's going to be 2 hard-coded paths here. There's a first watcher file path. And if this is not present, it's going to stop. And then they would execute the downloaded functions depending on a binary type. If it's binary type 1, they would be opening a binary at helper path, and they would spawn this one. If it's binary type 2, they're going to do the same, opening the binary at the bit path, and they would spawn it directly. Sorry, let's stay here. So essentially afterwards, the watcher is going to, the watcher is going to make sure that there's 2 additional binaries at both bit path and helper path are also executed in spawn. The one at helper is the one that we're already knowing about, which is the helper structure and functionality. The other one at bitpass is going to be the actual agent that is executed. Now, let's look at the start function. What we're going to see is the start function is going to start listening or like registering for device shutdown events. And if those shutdown events are going to be happening, it's going to make sure that the whole structure is going to stop and everything else disappears from the device. You remember that one of the first activities in Predator 2021 was actually that they were like stopping the shutdown in order to like still executing, but they left traces inside of shutdown lock. This is not going to happen with the Predator 2023 variant. And then afterwards, there's two additional activities that the watcher function is also executing. It's going to check agent on a timer, which is going to run a check agent function. And there is a monitoring crash reporter function. The check agent function should make sure that the agent is actually all the time running. And if the agent is not running, it would make sure that it's downloading it again and executing it. The monitoring crash reporter function is actually a little bit more interesting because it registered itself for a kernel queue to get kernel events. And any kernel event that there is a new crash log that is created, they would check if the crash log name contains system memory. And if it contains system memory, they would kill the memory maintenance D. The system memory reset events in crash logs that you can also find do contain a full list of all the running processes on the system. So this is likely a way of making sure they're not going to leave any traces behind in process lists. Now, let's look at the exact executed checks inside of check perform. And the first is the checking for country locale, and this time they're checking for both Israel and the US. And if they find any of those, they're going to report and abort. Afterwards, they're going to check for processes executing from temp. And if there is more than one process that is executing from temp, they would also report abort. But this also tells us, because one of the passes is like from the temp directory, that it's definitely checking for themselves. It's not like checking for themselves and anything else, but they're allowing one process to be executed from temp. So they're still running from that directory. Then they're checking if the console is attached, they would report abort. They're going to check for developer mode status, and if it's on, they're actually aborting, which is kind of interesting because developer mode could give them additional primitives on the device for exploitation. Then they're checking for is unsafe running, which is essentially a check for any kind of specific VPN apps, for jailbreak applications. One of the interesting tidbits is that they're actually checking if the device is check-rainable, but based on the definition of the sample, this is not applicable because it's running on ARM64E. And then they're checking if it's not a phone, which it has a couple of checks for like Corellium. And then they're going to report abort and checking if a proxy is running. All right. Some of the interesting parts here is it downloads an agent, it downloads the helper, it starts two processes, agent and helper, it runs the checks, it's going to listen for shutdown events, and it executes from private for temp. Now, let's quickly look at the helper, which gets initialized with the kernel memory read-write primitive. And then it's going to start. It's going to do the exact same thing as the watcher. It's going to listen for shutdown. And if it finds a shutdown event, it's going to make sure it stops and resolves. It's also going to start two specific functions. One is in check agent timer, which is doing the same to make sure that this agent is running on the device. And also it's going to check if a dedicated file at a file path exists. And if it finds that file, it's also going to stop. Which is kind of a kill switch situation. And the second thing that this one is doing is creating a first unit socket, then it's going to start a Unix socket server, and then it's going to create a listening Unix socket, and then at the very end it's going to process a request. Unfortunately, this is a little bit the end where the static analysis like dies, because the process request function takes in like remote procedure calls initiatives, and I don't know what is going to be called. I know a lot of the other code which is there, but I don't know what is the actual executed path because we don't have a link to this. Based on the rest of the code of the helper function and of the structure, there's a couple of potential operations that could be running. There's keylogger code. There is code for a camera enabler, which hooks media server D. There is code for VoIP recording, which hooks the same process. There's a DM hooker, there's a UM hooker, and a very interesting one, which is called NS Task Drop without developer mode, which seems to be some functionality of executing code in arbitrary different processes. In terms of the command line arguments that we could discover until now, we have pretty much 6 of the ones we have fully understood. Some of the other ones are still a little bit open to us. But what you can also see is that both the URL and the decryption material and also the names of the exact binaries on disk are transported over by the command line arguments. We just have some information of the directories where they would be executing, but we don't have a very concrete IOC. A couple of other interesting things that I saw is there is a lot of that in unreachable code. And very interestingly, there is a couple of information like an apply install D bypass or apply sandbox escape for others, and a lot of other like kernel code which is still reachable. Unfortunately, both the install D and the sandbox escape are like dead functions. There is no code in there. But it gives us some potential information of what they could be doing with that. Maybe they were actually installing an application on the system that could have been used as a persistence mechanism, similar to how Trollstore is doing it today as well. Maybe, maybe not. Interestingly, they also left a complete URL of a GitHub commit in there, so with some reference of the person that was developing the exploits. And they were checking for jailbreaks on remounting root partitions and for like check when devices, which was just not applicable for this one. In terms of the chain, we have now pretty much a good understanding of the loader, but unfortunately we don't have a good understanding of the kernel exploit yet. I know there's an implant, but I don't know if there's any persistency yet. So if we're comparing both the 2021, 2022, what we can see is we have now 3 processes which were executed in the 2023 variant. We don't know the exact process names anymore because they're like configurable by the arguments, but we have the directories, and one of those is private or temp. We don't know what kind of additional binaries would be used or what kind of additional injections would be done. Same for the responsible process. We don't know if there is any persistence mechanism, but we do know there's like 14 arguments. It gets a little bit more interesting in terms of how the binary actually changed in terms of the activity, because we're now detecting shutdowns. And they completely transitioned from using Python as their primary programming language and developed now everything locally in C, C++, and Objective-C. But they're still logging. There is still some interesting log messages that you could find, and we're going to disclose some of the log messages as well, so we can also use that for potential IOCs. In terms of locale checking, we have now the OS which is added, and still they're not removing any kind of that code. I would say probably 50% of the sample are actually not reachable from the current paths which are there. So there is a lot of additional stuff that it could give us some information on the primitives. In terms of cleanup and hiding, they have gotten a lot better. They're not killing maintenance or detecting shutdowns. They're probably going to remove crash logs, but not with the loader. They're going to do that with the agent later on, and they're going to spawn stuff still from private or temp. We still have a couple of open questions, like what is the kernel exploit? What is the functionality of all the kernel code which is in there? What is with a WebKit exploit? Persistency? And dynamic analysis is still a thing that I'm going to do once I have a proper device. Now, let's actually look at how we can detect the specific sample. One of the target data that we could have seen based on the sample analysis is actually we want to be able to detect files, and we want to be able to detect processes. And the data that we could use for that from a forensic standpoint is pretty much very much limited. In terms of the actual files inside of the temp directory, none of the sources that we have available are telling us anything about this. But we could use an app if we have the exact file paths to check for those file paths. In terms of processes, we do have indeed pretty much great sources because sysdiagnose and also some of the backup information are going to tell us a lot about this. So if we're translating this back into some of the mechanisms that we could use for this, then we can pretty much clearly see that something that I would call traditional detection methods, which would just be relying on an MDM and an app that runs on your phone, will absolutely fail at defining or detecting any new version of predator. If you want to detect predator in the wild, you need to work with forensic sources, such as a sysdiagnose and a backup, and you need to make sure that you're collecting those sources frequently and that you have scale technology to analyze those. Once you have found a sample or a dedicated path, obviously you can use your iOS app to check for that file path once you know it. But if you don't know that, you're never going to be able to find a new version of the specific sample. All right. Now, I want to spend 1 or 2 minutes at the very end to talk a little bit about security versus privacy. What we've seen on the Apple ecosystem is that there is a very delicate balancing that Apple needs to maintain. If you have too much security on a system, you're going to have pretty much good privacy, but you will have a lot less visibility for something like endpoint detection and response tools. And we can see this on iOS. We have pretty much strong security mechanisms for any kind of mass market malware, and the privacy of the user is very much respected, but we don't have the capabilities that we would need on an iOS application in order to find advanced malware such as Pegasus, Predator, Candiru, so on and so forth. Obviously, if we would have perfect security because we have a lot more visibility, we're also going to have a lot less privacy on the system. And there is going to be a delicate balance that Apple needs to find, but I don't think they have found that balance yet in terms of commercial spyware. I think lockdown mode is great for adding additional mitigations and prevention methods, but it's not going to help us find these commercial spyware samples. And we have seen in the past very, very often that those app uses and those attacks are still happening, even though Apple is adding mitigation over mitigation over mitigation. This is not stopping an advanced actor if they have the right vulnerability. So I think we're not going to get around that Apple needs to do something here. And just saying from a past experience, an endpoint security framework with the same capabilities that we would have on macOS, where it is allowed, would have found any commercial spyware in the last 10 years. Immediately. Which also gets me to my summary, because what we have seen is that threat actors have advanced exploits, but they're using stupid old standard implants like in 2010, in 25, something we have seen on Windows, on Linux, on macOS time over time again. Those are not even obfuscating. They're logging to the logs that they're running. This is something that would never be able to live on a standard desktop system on an enterprise device. But we are allowing those to run on iOS pretty much undetected by the majority. What we need to do as a defensive community in order to detect it, if Apple is not helping us, we need to scale the forensic data collection and the threat hunting process on it. And we're doing this way, way, way too less. We need to build better technology. We need to build better processes that are allowing us to work with people in order to get their data and to getting this into companies. Obviously, if iOS would give us an endpoint security framework, a lot of these problems could get away. And finally, there is to say, for this specific sample, there is a lot more to discover, and I'm not finished talking about it. I'm just not done with all the analysis yet. Last thing to say is, there's a couple of thanks and credits, obviously, for Kevin Hoganson, which is one of the members in my team, which did a lot of that initial work. He's unfortunately not able to be here to talk about it, but a lot of the credit definitely goes to him. And also to Amnesty International, Citizen Lab, Access Now, which are doing a lot of the groundwork to getting this research actually up and helping the community to detect commercial spyware. The same for Google Tag, Cisco Talos, and many of the other organizations in this field. Questions?
Hello. Yeah. So, as you just talked, that due to the privacy features that Apple has implemented, it is very hard to do forensics or even large-scale, at-scale threat hunting. But then there have been many cases where Apple has been informing some of their users, high-risk users, about potential exploitation of their iPhones. So they must be somehow collecting some telemetry at scale from their phones, right?
Yeah, so Apple did a lot of good work also on notifying potential victims, but very often we can only detect those samples months after they have been, or not even the samples, but the infections months after they have been running on the device. So the harm is still done. I want to get to a state where I can protect the user or detect it so fast that we can capture the sample, find the exploits, and patch it. I don't want to do this 2 months after it has been happening. So I do appreciate the work that is Apple putting into it, but I think this is just a starting point and we need to do a lot more.
Thanks.
Any more questions? Question coming.